In this video, we will discuss more about more examples on how to differentiate functions, find the derivative of a given function. And before we do that, let's refresh our memory on the functions. We know the derivative, right? We know how to the derivative of the elementary functions. So before we let's write down the derivatives uh, of uh, elementary functions. And the first one is the easy one. If you have a constant, c prime is always 0. And then we go to power function, which is x to a here. Prime is a times x to a minus 1, right? Then we learned how to differentiate exponential function. So e to x prime is e to x. And in general, we have uh, a to x prime is a to x times natural log of a, right? Then we discussed trig functions. We know that sine of x uh, prime is cosine of x, and cosine of x prime is negative sine of x. Then we have the derivative of tangent. Tangent of x prime is secant square of x. Right, so that's all the trig functions we need to know. We need to remember for the test or final exam, and then we discuss inverse functions using the implicit differentiation method. So we know that arc sine of x prime is 1 over square root 1 minus x squared, right? And also we know that arc tangent of x prime is 1 over 1 plus x squared. And one more thing here is the inverse of exponential function, natural log of x prime is 1 over x. So this is a complete list of derivatives we need to remember for the midterms and the final exam. So let's see a few more examples on how do we apply combining with all the rules we have, product rule, quotient rule, chain rule, and also uh, some methods, logarithmic differentiation. Let's try to combine everything together to differentiate a few functions. Let's see the first example here. It's an easy example. And first example here is let's try to differentiate y equal to natural log of absolute value of x. So if you have y equal to natural log of x, the domain is all positive numbers, right? But here we are taking all the absolute value of x. So the domain of this function is everything but 0, right? Is from negative infinity to 0, union from 0 to infinity, right? Put together as a set, which is everything but 0. You can write this as all the real numbers such that x is different from 0, right? So that's the domain of this function. Now we want to know uh, what's the derivative of this function, right? And but we do know this is true. Whenever x is positive, natural log of x prime is 1x, right? So let's try to, because we don't have a general formula on handle the derivative of absolute value, right? So let's try to write our function piecewise in two formulas. So we know that natural log of x as absolute value of x, this equal to natural log of x if x is positive, right? And if x is less than 0, the absolute value of x is negative x. So this is natural log of negative x, right? So let's try to differentiate them separately when x is greater than 0 or x is less than 0. So in this case, we know that natural log of x, this is when x is positive, so its prime is 1 over x. So that's our formula in the list, right? The other one, natural log of negative x prime. Now you can see that that is a composition of two functions, right? So outer function is a natural log, right? Inner function is multiplied by -1. So apply chain rule here, you get 1 over the inner function, that's the inner function, which is -x, times the derivative of inner function, which is -x prime, which is -1 here. So this is also -x, 1x, because -1 times -x is x, right? So no matter what happens, right, now you can see that no matter what happens, the derivative of absolute value of x, the absolute value of x is always 1 over x. So that's a generalized formula for the derivative of natural log of x. Not only for natural log of x, for natural log of the absolute value of x, this is always true. So let's see a few more examples, right? Example 1 here. Let's see example 2. Our function is y equal to natural log of e to negative x plus x times e to negative x. So let's try to differentiate this function here, right? So this is some function contains the natural log function, exponential function. You need to use chain rule and also the product rule, right? So let's try to write down the derivative out, right? Write it out. So we want clearly by look at this function here, we need to use a chain rule multiple times. And product rule, there's a product inside the natural log. We need to use product rule. And clearly we have to use sum rule. That's an easy rule to apply, right? So let's try to write down y prime in this case. So y prime. Look at, this is the outer function natural log. So the derivative of natural log is 1 over whatever inside. So this is 1 over e to negative x plus x e to negative x. Then times the derivative of the inner function times the derivative of this term, sum rule, right, which is e to negative x e to negative x prime, we have to use chain rule. Now the inner function is negative x, outer function is the exponential function whose derivative doesn't change, right? Then time the derivative inner function, which is -1, plus the derivative of this term here. We have to use product rule, right? X prime is 1, so you get e to negative x plus x times e to negative x times -1. So that's how do we differentiate this function contains yeah many terms, right? We can combine all the rules we have to differentiate such a function. Now let's see example 3. Example 3, we have y equal to it. Y equal to root x e to x squared minus x and times x plus 1 to the power 2 over 3. And that's a big product exponential, right? And so recall that, so you can use our product rule, chain rule directly, right? But recall that we can use logarithmic function to simplify such a function. So we have a new way to differentiate function, which is called the logarithmic differentiation. Right? And the steps are take a natural log first because natural log is good at simplifying product or quotient or exponent, right? Make it to be a much easier function. And then you can apply implicit differentiation to differentiate to get y prime, right? So let's do that. So get natural log of y is natural log of square root x times e to x squared minus x times x plus 1 to the power 2 over 3, right? So we do not differentiate now because now is, yeah, it's not simplified yet, right? Remember that the logarithmic function can change from a product to sum. So this is natural log of the first factor, root x, plus natural log of second factor, e to x squared minus x, plus natural log of third factor, which is x plus 1 to the power 2 over 3. Right? Then you can bring down the exponent. So the first term is 1 over 2 natural log of x. That's much easier to differentiate. Plus x squared minus x times natural log of e, which is 1, right? Plus 2 over 3 natural log of x plus 1. Right? Simplify one more step. We can get rid of that actual constant plus x squared minus x plus 2 over 3 natural log of x plus 1. Right, this is natural log of y. So taking some work to simplify this big natural log function. But after we simplify, we get a much easier equation. Natural log of y equal to that. Then you apply implicit differentiation, right? The derivative left side is apply chain rule, right? Differentiate both sides of this equation here. Left side, apply chain rule, alter function in natural log to get 1 over y times y prime, right? The right side, the first term is 1 over 2 times 1x. Second term is 2x. Third term is minus 1, then plus 2 over 3 natural log of x plus 1. The natural x1 prime is 1 times 1. That's it, right? So we get y prime is y times the right side, right? Y is root x e to x squared minus x plus 1 to the power 2 over 3, 1 over 2x plus 2x minus 1 plus 2 over 3. Wait, I made a mistake, right? Natural log of x plus 1 derivative should be uh, should be 1 over x plus 1, right? Times 1 over x plus 1 here times 1 over x plus 1. So that's the final answer for this problem using the method of logarithmic differentiation. Now let's see one more example, example 4 here. We have another kind of complicated function, which is this, right? So we have y equal to tangent of x, then to the power 1 over x, right? We want to find y prime. I can see that such a function, you cannot apply a chain rule or any rule we have so far directly. You have to change that form, right? How do you change it? Because this function is not a simple exponent function or some compositions, right? So it's x is in both position of the base and exponent. So how do we simplify that? We know that natural log is also a good operation to simplify this kind of function, right? So we want to use logarithmic differentiation. Logarithmic differentiation. So we take a natural log. Natural log of y is natural log of tangent of x, and then this thing here to the power 1 over x, right? Remember, this natural log can bring the exponent down, right? So this is equal to 1 over x, natural log of tangent of x, right? And this is a quotient, which is natural log of tangent of x over x, right? So now let's try to differentiate both sides of this equation. Left side, if you apply this method, logarithmic differentiation, left side is always natural log of y. The right side is a simplified function, right? You need to change from a product in natural log to a sum of natural logs, or a quotient to difference, or exponent to bring the exponent down, right? And so if you differentiate this both sides, left side is always 1 over y times y prime. Now right side here, we have to use quotient rule, right? That's a quotient and also chain rule. because numerator is the composition of two functions. So x squared is the denominator. Numerator first term is the derivative of natural log of tangent of x. You get 1 over tangent of x times tangent prime, which is secant square of x, and then plus the numerator times the derivative of the denominator. The derivative of the denominator is 1, so get natural log of tangent of x times 1. So you get y prime is what? Is y, which is tangent of x to the power 1 over x time this big function we just found. So x squared 1 over tangent of x time secant square of x plus natural log of tangent of x. So that's how do we differentiate this kind of uh, function, right? And so, yeah, apply the method called logarithmic differentiation. Always simplify your function by taking natural log both sides, then differentiate. That's much easier than you have to change your function to a different form to differentiate, right? Apply a chain rule or whatever. Final answer will be the same, but this one is more straightforward.